Hi everyone, this is going to be your last recording for the week. We are finishing up lesson 1 today. Just a reminder, I will be out testing the whole week, so if you do need me, please email. By the end of the week, you should have completed your lesson 1 journal and your lesson 1 quiz after you have watched all 3 recordings or videos and completed the activities for each day. So please keep an eye on the announcements. Let me go ahead and show our learning targets. So on Monday, you guys watched a video where you learned how to identify special segments and lines and circles, including radii, diameter, chords, secants, and tangents. You also were able to explain that 2 circles with the same radius are congruent. And then in yesterday's recording, we used properties of lines tangent to a circle to solve problems. So that leaves the last target for today. And we will be identifying common tangent lines, including common internal and common external. And we will be using them to solve the problems. So what I first want to talk about are the vocabulary words for today. And that includes tangent lines to circles and circles tangent to each other. So we're first going to talk about tangent lines to circles. We have 2 types. We have common internal tangents and we have common external tangents. So if we connect 2 radii of a circle, you can see this dotted line here in each diagram. Our common internal tangents intersect the line segment containing the centers of the 2 circles. So if we have circle A and circle B, then this red line, we can call it line L, or we can name it by 2 points on the line. We can say this is C, D. So we see our common internal tangent intersecting the segments connecting the 2 centers of our circle is our common internal tangent line CD, or we can call it line L. Okay, in the next diagram we have common external tangents. Notice a common external tangent does not intersect the segment containing the 2 segments of the circle. So I can call this line M, or I can call it, let's say, E, F. So a common external tangent does not intersect the segment connecting the 2 circles. So if we were to name our common external segment, we would say line EF or line M. So let's look at the next figure and figure out how many common internal tangents that we see. So remember, the definition of a common internal tangent is that they intersect through the segment containing the 2 centers of the circle. So if I connect these 2 segments, or these 2 centers, the internal common tangents are those tangents passing through that dotted yellow line. So we can see that there are 2. We have this line here, and we have this line here. They are both tangent to both circles, so that makes them common. And because they pass through the line connecting the segments, or the segment connecting the centers of the circle, that yellow dotted line, it passes through that, we say they are internal common tangents. So how many are there? There are 2. Now let's look at the same figure and identify how many common external tangents that we have. So remember, by definition, a common external tangent does not pass through the segment connecting the 2 centers of the circle. And so in this case, we see that we also have 2, but it's going to be this green tangent and this green tangent. So how many common external tangents do we have here? We have 2. Next, I want to do an example where we can use common external tangents. So here I give you two circles, circle A and circle B, and I want to find the distance between the centers of the circle in the figure. So using our diagram, let's draw a segment in that joins the center of these two circles, because that's the distance we are looking for. Okay, so I'm going to draw a segment containing A and B. That blue distance, AB, is what we are looking for. All right, so we know that DC is tangent to both circles, the common external tangent, because it is intersecting each circle at exactly one point, point D for circle A and point C for circle B. So because it is drawn tangent to the circles at each of the radii, we can see radii DA and CB, we know that it forms 90-degree angles at those 2 points. So this is 90 degrees and this is 90 degrees. What we can also do is we can draw in a perpendicular line from our center A, perpendicular to radius CB, and that is also a 90-degree angle. And so now we see that we have a rectangle. If I label this point here as point E, then I have a rectangle DCEA. So we can determine that EC is equal to AD. So AD is this yellow segment here, which is 15. So that means CE is also 15. So now we can figure out the length from B to E. And that length is just going to be this part right here. We know the whole segment of BC is 25. That's given in the diagram, this value right here. So BC equals 25. And I know that CE is equal to 15. So if I subtract those two, that will give me the length from B to E. So we have to take BC and subtract off CE, which is 25 minus 15. So that tells us that BE has a length of 10. So now what we can do, I'm going to grab this triangle here, this right triangle that we've formed, this purple one. I'm going to redraw it down here so it's easier to see. So this is point A, this is point B. We're looking for the distance between the two, between the two of them. Sorry, this is B, and this is E. And we've determined that BE is 10. This is a 90-degree angle, and we can tell that AE is the same as D to C, so this is 40. So now we can use the Pythagorean theorem. We can say that these two sides here make up the legs of our triangle, this one and this one. So if we square each and add them together, we have AE squared plus BE squared. That gives us the length from A to B squared. And plugging in those values, AE is 40, so 40 squared, plus BE is 10 squared. That is going to equal AB squared. So now we can just simplify. 40 squared is 1600. 10 squared is 100. That is equal to AB squared. So I'm going to come up here where I have more room. 1600 plus 100 is 1700. That is equal to the length from A to B squared. So to figure out the length of AB, I just take the square root of 1700. And that gives me approximately 41.2. 41.2 inches. So there is an example using common external tangents. The last example I want to do with you guys is using common internal tangents. So that's the next one we're going to take a look at. All right, so here we're given two circles, and our common internal tangents, remember, are the ones that intersect the line containing the two segments of the circle. So our internal tangents would be BA and CD. And we're going to do this example using similar triangles. So we are told that segment AB is tangent to both circles. We want to find the value of x. That's going to be this length over here, or the radius of circle BD, or of circle D, the radius BD, and we want to find the distance between the centers of the circle. So that's between point C and D. So the first thing we're going to do is we're going to prove that these triangles are similar. So this will take us back to what we finished up geometry A with. Because we have tangents perpendicular to radii in our triangle, we can say that AC is perpendicular to AB. So let me color code those for us. AC is this radius that is perpendicular to this tangent. So I can say the tangent is perpendicular to the radius. I can also say that BD is perpendicular to that same line AB. Why can I say that? Well, BD is this radius over here, and it is forming a 90-degree angle with the common tangent. So therefore, those lines are perpendicular from the same reason as above. So I can just copy that same one down. I'll put C above. Okay, so we've shown that we have two 90-degree angles in each of our triangles, right? So we can also identify another congruent pair of angles, and that would be CEA and BED, because those are, if you remember, angles formed by intersecting lines that are opposite of each other. So those are vertical angles, right? So I could say angle CEA is congruent to angle BED by the vertical angle theorem. And just to make it a little bit more complete, because I showed CAE and DBE both equaling 90, I'm just going to state that above. I'm going to say angle CAE must therefore be congruent to angle DBE because they are both right angles. Or you could use the right angle congruence theorem. So now if you notice, I've shown two angles in one triangle congruent to two angles of the other. So we've really used, if you think back to ways we showed triangles were congruent, or I'm sorry, triangles were similar, we had one of our methods was angle-angle similarity. So I can say angle CEA is similar to triangle DEB by the angle-angle similarity postulate. That'll take us back to Unit 7 from last semester. But now that we've proved that the two triangles are similar, you guys can use this going forward to help us solve for x. So using our similar triangles, we can set up a proportion. I can say AC, that's the first and third letter. So AC is to the first and third letter of the second triangle, BD. BD, that has to equal AE, so the third and the second, and the third and the second. So this is going to be AE over BE. And when I plug these values in, from A to C is 5. From B to D, that's X. That's what I want to find. That's going to equal from A to E, which is 8, over B to E, which is 12. And remember, to solve proportions, we cross multiply. So I can say 12 times 5 has to equal 8 times X. Well, 12 times 5 is 60. So that's 60 is equal to 8X. And if I divide by 8 on both sides, then I get X is equal to 7.5. 7.5. So we've done the first part of the problem. We have found the value of X to be 7.5. Okay, so you guys might want to take a quick screenshot of this. And then we're going to go on to finding the distance between the two centers. You can probably imagine how we're going to do that. Each of those triangles are right triangles. So I should be able to use the Pythagorean theorem to find each hypotenuse length. And then we're just going to add those together to get the entire length from C to D. So I'm going to clear the page and write in what we just solved for. We just found that X was equal to 7.5. And remember, my goal next is to find the distance between the two centers, which is formed by CE, the hypotenuse of one triangle, and DE, the hypotenuse of the second triangle. And I've already determined that these two were the right angles. So we're going to use the Pythagorean theorem twice. I'm going to do CA squared plus AE squared. CA squared plus AE squared is equal to CE squared. That's our hypotenuse. And I'm going to do BE squared plus BD squared. And that's going to give me ED squared. Once I do that, then I can add the two lengths together to find the total distance between point C and point D. So doing this, I know CA is 5, so we have 5 squared, plus AE is 8, plus 8 squared equals CE squared. Well, 5 squared is 25, 8 squared is 64. So 25 plus 64 gives me 89. So 89 is equal to CE squared. So CE must equal the square root of 89. And if I take the square root of 89, I get about 9.43. So that's this length here, 9.43. Now I'm going to repeat the process using the second triangle over here. The two legs of that triangle are BD and BE. So those two segments squared and added together give us the length of the hypotenuse, ED. So BE is 12, so 12 squared plus BD is 7.5, so 7.5 squared, that's going to equal E to D squared. Well, 12 squared is 144. 7.5 squared is 56.25, and that's going to equal ED squared. So if I add those together, 144 plus 56.25, I get 200.25 is equal to ED squared. So I take the square root of both sides. And that gives me that ED is approximately equal to 14.15. So that's this length right here. So now we can come over here and we can find the distance from the two centers of the circle. So CD is what we're looking for. That is just CE plus ED. So CE was 9.43. ED was 14.15. And so that gives us our entire length, 9.43 plus 14.15, to be about 23.58 units. So now that we have seen a couple of examples using common internal and common external tangents, I'm going to just go over a couple more vocabulary terms, and that will wrap up lesson 1 for this week. So two circles can be tangent to each other if they have only one common point. So you can see on the left we have, let's say, circle A, circle B. These circles are what we call tangents because they only intersect at one point. One common point. So we say they are tangents. Two circles have two common intersection points if they intersect each other. So we can see here this one and this one, two common points. And those are called intersecting circles. And then finally, the last two terms I want to show you guys are when circles can be externally tangents. And that is if they are situated outside of one another. So external, think outside. And those are the ones that have one common point between them, but the circles do not, I guess, overlap each other. They're both their own unique circles. They can also be internally tangents if one of them is situated inside the other. So we say internally tangent, they're still intersecting at one point, but one circle is sitting inside of the other circle. And so that is what internally tangent means. So I want to thank you guys for watching your three relatively short. I know yesterday's was a little bit longer. Please make sure you're completing your activities for each day, and then that gives you a full day tomorrow, which will let you work on actually tomorrow, Thursday, and Friday of this week, which will allow you to complete your Lesson 1 quiz and your Lesson 1 journal. So please email me if you guys have any questions at all, and I hope you are having a great week.